Maybe I can first introduce our speaker. Today, our speaker is Laurence Tratt. Dr. Tratt is currently a reader at King's College London. He's also leading the software development team. Also, he is a consultant of our Edinburgh team. His work is mainly about programming language, in particular about real-world issues of language design, including parsers and metaprogramming, language composition, and language virtual machines. And today he'll talk about implementation issues of language virtual machines. So please, Laurence.
Thank you very much, and good morning and good afternoon and evening to you, wherever you are. I know we've got people in various parts of the world, and thank you for the introduction. What I thought I'd talk to you about today are assumptions that I see people who are implementing programming language virtual machines making. So just to be clear, I'm talking about things like the Java virtual machine, the JVM, or PyPy or CPython, or those sorts of things. Nothing in here is about Docker or anything like that. It's all about programming language virtual machines. And what I'm going to do is go through some assumptions that I see VM developers making implicitly or explicitly, and some of the consequences of those assumptions. And I'm going to try, when I can, to tie this back to ahead of time compiled languages, so C or C++, or perhaps more like languages that are under current development. Please feel free to ask questions as we're going along. I'm very happy to take questions. So the whole motivation for this talk is that I wake up sometimes in the middle of the night and worry, what happens if we're wrong about what we're doing? And I think it's good to rethink and be explicit about our assumptions and challenge and tackle them. So what I'm going to do is give you a few assumptions and some of the consequences. And I'm going to start with a really simple one to warm us up, which is the idea that VM development is a destination, or indeed language implementation in general is a destination. So imagine I've got this very simple graph, and I've got on the x-axis time, how much time I've spent implementing my language, and on the y-axis, I've got how complete my language implementation is. And let's imagine I start a new language implementation from scratch. When I started, I often think, I am going to do this amazingly well, it's going to be really great. But what happens is, a lot of time passes, and not much seems to happen. And it's very easy to get depressed and project forward and think, at this rate, I am never going to get finished. My language doesn't implement very much, it doesn't do much, but soon we get an inflection point. And what happens is all of the early work we put into the background of the implementation, all of the stuff getting debugging tools and portability and general libraries up and running, suddenly starts paying off, and we enter this happy period where every new day makes more and more programs in our language run. And at that point, it's possible to completely flip from earlier, project ahead and say, at this rate, not only will I be complete soon, but I will be more than complete. I will be 110% complete or whatever. But then there's a second inflection point. And at that point, the language is sort of getting increasingly complete, but we start getting to the point where we get into smaller things, more and more optimizations, bug fixes. And experienced programming language implementers realize that they're asymptotically reaching, but never quite getting to perfection. And it's a sort of endless struggle. And you can see that if you look at some of the open source language implementations. So this is a little GitHub snapshot from a little while ago for Rust. And you can see at that point it had 5,000 open issues. It has a lot more now, and 198 pull requests. And this shows you what happens when you language implementation becomes more mature. There are lots of people filing problems with it. Some of those are real problems that you want to fix. Many of them are incorrect problems where people have misunderstood things. People are filing pull requests where sometimes they're adding new features or adding optimizations. And sometimes some of those are making the implementation better. Some of those are pulling us off track into ways that we never really wanted. And ultimately, I think the important thing that we have to remember here is that language implementation in general, and VM development specifically, is a never-ending process. And sometimes people get depressed by that because they think, oh, wouldn't it be nice to work on a project that's complete? You can look at it another way. It's jobs for life or a never-ending stream of interesting challenges. So that's our first easy assumption. Let's move on to one that I think is a little more challenging, which is the notion, and I think that this is a term I've invented for better or worse, which is that we know where the performance ceiling is. So imagine I've got a program P. What is the fastest that that program P could possibly run if all the implementation is able to perfectly optimize it? Well, it's a hard question to answer, because imagine I've made a new implementation, which I'll call me. Then, and I love this, the fact that I have a graph with one axis, because it's easy to think about. Once I've got my program running, all I know is that the maximum performance of that program at the moment could be however fast I've got it to run. Now, if I'm lucky and I've got a language that has multiple implementations, then if I run my program on another implementation, I may realize that actually my program could run faster. And the good thing about this is it tells me, okay, I've got work to do. I could further optimize my program. I could get at least as fast as other one. And if I find another implementation and it's a little slower, then that doesn't change my idea of where the performance ceiling is. What's troubling is that I'm never quite sure if I'm going to find another implementation which is faster again, raising my idea of what the performance ceiling is, and meaning that I now know I have more work to do. And what happens if there are further and further elements up? And the thing that keeps me awake at night is the worry that there's some other implementation or some way of implementing my language that's so much faster that it totally changes my idea of the scale of performance. And what this shows to me is that our notion of performance is almost always relative. I know that my implementation is 10% faster or 10% slower than another implementation, but I don't know if it's within 10% of the absolute best performance possible. Outside of one or two rare situations, for example, super optimization, where you can take very small loops and optimize them sort of provably to some extent as fast as they can do. And I think that this means we need a certain humility when implementing our languages, because we don't really know how well we're doing. And I'm going to come back to this concept a little later. Excuse me. So let's go to another assumption that people make, which is that we're good at optimizing abstractions. Most optimizations in compilers, just-in-time compilers or ahead-of-time compilers, are, if we're being honest, ad hoc and/or unpredictable from a user's perspective. Let me take a very classic optimization that you'll find in JavaScript virtual machines. So this is something that you'll find in, say, V8, the JavaScript VM in Chrome. When you've got a call citer that looks like O.m, so I'm calling a method M on an object O, I don't know which particular implementation of M will be called at runtime, because there could be many classes and subclasses, and so it's who knows which one of those methods M will actually be called. But so most just-in-time compilers will start by assuming that the same method M is always called at the same point in the program. They'll optimize the monomorphic call site. They'll inline it. They'll heavily optimize it. But that assumption might turn out to be wrong. And maybe actually we call 2 or 3 different versions of M. And if that happens, we slightly downgrade the optimization to polymorphic call sites, which is not as well optimized, but is a little bit better if you've got multiple call sites. And then if you have lots of different method M's that you end up calling, eventually it downgrades to a very slow generic version of that called a megamorphic call site. Roughly speaking, in most VMs that have this sort of optimization, you go from monomorphic to polymorphic when you go from 1 to 2 calls, and polymorphic to megamorphic when you go from about 4 to 5 calls, roughly speaking. Now, this is a really good optimization. It makes a lot of sense. There's actually a fairly good bit of evidence behind it that it's the right thing to do. But if you're a user, you write a program, and it is running in the monomorphic phase of things, it runs really fast. You make some small change, and suddenly it may go to megamorphic, and you'll get a huge slowdown, 4, 5, maybe even 10x or more. And that's very, very surprising, because we don't really have a good way of communicating optimizations to users. In fact, generally, we don't even really try. Try finding documentation for your favorite language that says, we pretty much guarantee to optimize this statement or series of statements to this. It doesn't happen. What happens instead is that there's a sort of folklore where we communicate amongst ourselves saying, by the way, do you know if you rewrite that statement to something else, the compiler will better optimize it? And this is a real challenge because most users don't know how to write programs that the compilers will optimize well. They're just kind of flailing in the dark and hoping that things work. And when the program doesn't run fast, they're generally unable to work out why. Things like Compiler Explorer, which I'm sure many of you use, are a great way of understanding how small programs are optimized, but it doesn't really scale up to larger ones, and it's a big problem. And I think this is something where we've put very little effort into it, and users are very confused, and I think we could do better if we tried harder. So, our next assumption, which is that we know what the impact of individual features in language implementations are. So if you look inside virtual machines, like a lot of JavaScript VMs or VMs for other languages, you'll see that they often use pointer tagging. So it's a very classic representation optimization. If I'm on a 64-bit machine, all of my pointers on the heap are going to be aligned to 8 bytes, which means I've got 3 spare bits in a pointer that never are set to 1. So I can then use those to differentiate, say, an integer or even a small string from a pointer. That means that I can do things like not allocate memory on the heap and try and reduce pressure on the memory bus and so on that way. It looks and sounds like a very appealing optimization, but there's only one published study I know of that looks at pointer tagging, and it shows that it has no measurable effect. Now, it's on a very small VM. I know of another unpublished study that also shows pointer tagging has no effect. Why is this? Well, by the time people have created a large VM, it's generally too difficult to turn pointer tagging off and back on again to understand whether it was worthwhile. The assumption that it would help is built in from the very beginning. And that means that we actually really don't know if it works or not. My gut feeling is that it probably does help, because I think that for languages where you've got, say, arbitrary sized integers, where they can grow to an arbitrary size and ultimately potentially end up on the heap, most integers won't need to be that big and are better represented inside a single machine word. But all I have is my gut feeling. I have no evidence to back up that pointer tagging is actually an effective optimization. And if you look inside virtual machines, there are really only 2 areas that have been fairly heavily studied: garbage collection and register allocation. But if you go and talk to garbage collection people, both in industry and academia, you'll realize that actually we still don't know an awful lot of things about it. There are huge numbers of open questions. We don't even know which of the basic approaches to garbage collection is the right one, conservative versus precise. We don't know the trade-offs. There are new papers published on register allocation every year. And this makes me curious, because if those are the topics we best understand and there are still many open questions, imagine how many other things we really don't know very much about. And one of the problems is that we're often trying to benchmark things to understand the effects of an optimization or a change to our VM, but there are other impacting features that we're not aware of. So for example, if I'm starting to benchmark a program, then it does something odd, then people often say, oh, that's the program doesn't have good cache behavior, or the program interacts badly with the branch predictor. Now, in my opinion, yes, some programs do have bad and inappropriate cache behavior that can be fixed. Some of them do interact badly with the branch predictor. But when people blame caches and branch predictors, most of the time, I think they're really saying, we don't have a clue what's going on, so we're going to blame these magic things over here and pretend that it's their fault and not ours. I think mostly it means we don't know what we're doing. And there are some other weirder things. A few years ago, we did what I think is still the largest, most detailed programming language benchmark experiment anyone's ever done. And one of the things we ended up doing was recording the temperature of the processor during benchmarking. And what we found is about 1% of benchmarks, the CPU was overheating and clocking down. When it clocks down, you're going to get, depending on the processor, anywhere from a 2 to 4x performance decrease. Now, if that happens when you're benchmarking something, it's going to completely change your view of the effectiveness of an optimization or feature. And it happens often enough that it's a problem. And that's just the temperature in the processor, which is very easy to read. And most Intel processors, for example, even have a little flag telling you, yes, I clocked down since you last checked. what's the effective temperature on, say, RAM or some parts of the motherboard of the performance and benchmarking? I have no idea. I don't think anyone does. So there are all sorts of things that can interfere with our understanding of how our programs are behaving. Then there's the operating system. I often read papers that say, I benchmarked my language implementation on a laptop. And when someone says that, that what they mean is they ran their benchmarks whilst they were running YouTube and probably playing a game at the same time. The numbers we get out from that are totally unreliable. Plus, laptops overheat more often than servers. But even if you try and be really clever and benchmark on an unloaded server, there's still other processes running. You're still going to have context switches which interfere with performance evaluations. And it's very hard to fully factor out all of those things. And then, of course, inside a virtual machine itself, and this partly goes for even
Muted.
Of languages like C, you've got various heuristics that are happening. So inside a just-in-time compiling virtual machine, you've got heuristics that say things like, should I choose to compile this method? Well, I'll do it based on how often it's been called. And that might be a number, 10, 50, 100, or whatever. But often there's multiple heuristics that choose whether a method is compiled or recompiled. How do they interact? Well, it turns out mostly we don't know. And then you've got things like the heuristics for when to garbage collect. Those are complicated as well. And when you combine, say, compilation and garbage collection heuristics, oh boy, like no one knows how these actually affect behavior. And there are quite a lot of other ones. And we ended up observing an outcome which I've ended up calling, and this is, I apologize again, is another term I think I've invented, performance non-determinism. In other words, I run the same program twice and it behaves from a performance perspective differently each time. Still produces the same answer at the end, but may take longer to get there. And that confused me for a long time before I realized that there are some simple explanations for some of the performance non-determinism. So let me give you a very simple example. Imagine I've got a program and I just observe it running over time, and I observe, say, how often garbage collection happens. So let's say garbage collection happens at a fixed tick rate whilst I'm running my program. And let's imagine inside my virtual machine, there's some other thing happening at a fixed tick rate, different from the one above, but say compilation, profiling, something like that. Both of those are fairly small events, and I probably won't notice their impact on performance whilst they're happening. But if you've got things happening at fixed tick rates, you find that every so often they combine together. And then when they combine together, in that little red line you can see here, you suddenly get weird spikes in your performance that you can notice, measure, and be very, very confused by. Now, obviously, this is a gross simplification, but this sort of thing, it appears, happens quite regularly. And I have a counterintuitive suggestion for how to lessen the effects of performance non-determinism of this kind, which is that in many cases, we would do better to introduce more non-determinism. For example, instead of saying, I'll compile a method when it's been called 52 times or whatever, it might be better to say, I'll compile a method when it's been called 52 times plus or minus random 10%. So now I'm hoping that I spread out the noise inside my process so it doesn't all bunch up at occasional points, but is filtered out a little more averaged out across the process run. It's an idea. No one's tried doing this yet, but it's the sort of example where we might be able to think differently and get some good effects that we're currently unable to do. Let's move on to our next assumption, which is we understand how large systems perform. So as I mentioned earlier, we did this very large-scale programming language benchmark experiment a few years ago. And here's one graph from that. So here's how to read this. This is the Richards benchmark running on hotspot on a Linux server. On the x-axis, we put the benchmark in a for loop for 2,000 times. So that's each iteration of the benchmark. And on the y-axis, you can see the time in seconds for how long each iteration of the benchmark took to run. And what might not be obvious is that if you look up in the top left, the benchmark started off slow and was, on the first iteration, optimized very effectively, and then it became fast for 200 iterations. At the 200th iteration, something happened, and then it got 5% slower. Now, That doesn't look like it's supposed to happen inside a just-in-time compiling virtual machine. Things get much more amusing when you realize that Richards is probably the most important single benchmark to Hotspot. It's the benchmark they've used since day 0 to measure the performance of Hotspot. No one ran it long enough to see that it gets slower over time. And I know because we did a bit of investigation that what happens is that the 200th iteration, Hotspot decides to recompile the program, which is why you can see a temporary slowdown, and makes things worse. Now, is 5% performance decrease a big deal? Yeah, definitely. People will spend years of their lives trying to get a 5% speed increase inside a virtual machine. This is a huge deal. And when we looked at it, roughly speaking, half of VM benchmark pairs showed these sorts of problems, at least sometimes, and in many cases, they showed it all of the time. And we published this work and have talked to all of the people in the virtual machine community, and they've all gone, yeah, okay, we can see there's a problem here, but it's okay. We know that micro benchmarks behave poorly. It's a known problem. And that's okay because it doesn't affect real programs. We know that it doesn't. And the first time someone said that to me, I was very surprised. It seemed hard to work out. By about the 7th time someone said that to me, I had an answer, which is, that's a really convenient explanation. What you're saying is when we can measure something, we can show you there's a problem. When we can't measure something properly, you're saying there isn't a problem. That seems very unlikely. In particular, if that's true, it would break the idea of compositionality. In other words, big programs, large systems, are composed in a sense of multiple small programs. For example, imagine that I had a large program that had the Richards benchmark as some little part of it. The chances are inside, if you were to run that combined program on Hotspot, the Richards part of the program would still show that slowdown that we saw earlier. But it might well be lost in the noise of the large system, because the large system will also have ups and downs. It doesn't mean that that subpart of the program isn't behaving poorly and less well than we think it should. In fact, I'm convinced it probably is behaving worse than we think it should. So in other words, I think our large systems on VMs are being much less effectively optimized than we expect. But we can't tell because we've
the volume down on the PC
inside the
no
white
effect.
box and understand the performance of these things. And I think it would be good if we could apply the same sort of techniques we could at a black box level to a white box level. And I think we'd see that large systems are behaving quite badly. Did I hear a question from someone? If you would like to ask questions, please do. Nope. Okay, cool. Please ask questions when you would like. Okay. So this is our next assumption, and it's all based on the fact that virtual machines, in fact, any language implementation is incredibly expensive to create, as I think you probably realize and are starting to find out. To give you a rough idea, Hotspot, so that's the standard Java virtual machine, the one that we all use when we use Java, has had anywhere from between about 1,000 to 4,000 person years of effort put into it. And from that, you can probably derive how many dollars it took to create. It took a lot of money. And it shows it's a really good virtual machine. But people look at that and say, well, wow, I'm making a new language implementation. I don't want to spend all that. Why don't I reuse the existing hard work of an existing virtual machine or of LLVM or something like that? And that's a very appealing. The benefit that those into their optimal. It doesn't always work. And the classic example of this is CPython and Jython. So CPython is the standard version of Python that you'll download if you go to python.org. It's the version of Python everyone uses, basically. It's a standard C interpreter. It's not bad, but it's not amazingly clever. It's not particularly fast. Jython is Python running on the JVM. And it has access to all of Hotspot's amazing optimizations. And I really want to emphasize, Hotspot is amazing. But when I last measured it, Jython ran at half the speed of CPython. And since I last did that, CPython has increased its speed and I'm pretty certain that Jython hasn't. So why is Jython so much slower than CPython when Jython appears to have all the advantages? Well, it comes down ultimately to a problem that we end up calling the semantic mismatch. When you have instruction sets, they tend towards the generic or the specific. So to give a concrete example, we all know if we've got the x86 instruction set, it's very generic. It doesn't have anything particularly aimed at implementing one programming language or another. But the good news is you can translate nearly any language you want into x86 and get good performance. The bad news is that translation is often very difficult and requires huge amounts of knowledge to encode all your language's semantics in terms of this generic instruction set. At the other end of the spectrum, you've got things like Python or Java bytecode. Those are tailored at one language, in the case of Python, or in the case of JVM bytecode, at a family of languages that all look roughly the same as each other. This makes it much easier to write a compiler. It makes it much easier for virtual machines as well, but that's a little bit by the by. It makes the implementations a lot cheaper to create. And when your language that you want to translate into works inside those bytecodes, everything is good. But imagine if, for example, you want to implement a language that uses a feature you haven't got an easy version of. My classic example of this are continuations. If you've got a language with continuations and you want to implement it on the JVM, then at least until recently, the JVM has no direct support for continuations. You have to encode it in some other ways, and some implementations have very entertainingly amusing ways of doing this. Some of them do things like create a thread for every function call. The performance is horrible beyond belief. I mean, it's comically slow. And okay, we could say, right, well, let's add continuations to the JVM. I think they're actually doing that at the moment. But it doesn't matter if you fix that feature. There'll be another feature that some language wants, which isn't in your language bytecode, and that you will always end up not quite having all of these features that you might want. There's always some sort of semantic mismatch between the new language you're implementing and your language-specific bytecodes that you already have. One approach that people take is to try and move the bytecode for different languages, in sense, gobble up the features from one to another. So the classic example of this is the invoke dynamic bytecode in the JVM. This is specifically aimed to help languages like Python and Ruby. And simplifying a little bit, it tries to make it possible for these languages to better optimize dynamic function calls, because those are something that the JVM normally does very badly. And invoke dynamic has a wonderful story to tell, and everyone says it's going to fix the performance problem. And they've been saying that for about 15 years, and it hasn't fixed the performance problem yet. And I confidently state that it probably never will, because again, it's trying to give you a generic optimization by being specific, and you can only do one or the other. Another solution that some languages take are to tweak the language design. So the main example I'm aware of here is Scala. So for those of you who don't know, Scala is a functional language, and it runs on the Java virtual machine. And it's always been intended from day one to work on the JVM. And they changed the language design based on their understanding of the performance of the JVM so that Scala would always run fast. For example, Scala has the concept of null, which I'm pretty convinced they wouldn't have had if they didn't want to run on the JVM. And there are some other language design changes that are in Scala from day one. And they do work. They make Scala work quite well on the JVM when otherwise it probably wouldn't. But this only works if you can redesign your language from day one to fit the performance model and language semantics of your target platform. At the moment, an awful lot of people are very excited by WASM. So this is WebAssembly. For those of you who aren't fully aware of this, it's a sort of bytecode interchange format for programming languages that works on the web. And most of the browsers have fairly good implementations of WASM now. It's a kind of language-independent bytecode, let's say. And it runs really well, provided your language looks like C++. And people keep saying it'll implement every other language well. Well, at the moment, WASM doesn't even have support for garbage collection in any meaningful sense. So most languages, if you translate them to WASM, will be incredibly slow. And this isn't really WASM's fault. WASM, again, is somewhat specific. It's not a fully generic system, because if you do that, you have security problems, and WASM's trying to avoid those. So WASM is not going to suddenly make every programming language run as fast as every other programming language. It's just not a silver bullet. It can't possibly work. There is another technique, and I'll talk about this a little more at the end, which are the meta virtual machines. And there are two approaches to this. There's dynamic partial evaluation in the truffle Graal system from Oracle. And there is meta tracing, which has quite a long history, but the best known example of this is PyPy/RPython. In both of these systems, you implement an interpreter and you get a just-in-time compiler for free. This means that you can somewhat customize the optimizations that your interpreter and JIT make based on your language semantics. It's not a complete free-for-all. It doesn't solve all the problems, but it's probably the best overall solution we know at the moment to making arbitrary languages run fast. Let's move on to another assumption, which is all to do with benchmarking. So as part of that benchmarking work I talked about earlier, a few years ago I downloaded what was then, and probably maybe even still now, is the best known JavaScript benchmark suite, Optane. So it's a large benchmark suite created by the V8 team at Google, has a number of large JavaScript benchmarks, and is widely being used to understand the performance of JavaScript VMs. And I downloaded the benchmark suite, and literally the first thing I did, and by the way, I really don't know JavaScript very well, I just put each benchmark in the benchmark suite into a loop to make them run longer. And the first thing that happened is one of the benchmarks caused the virtual machine to run out of memory. And I looked at it, and it turned out that, yes, the benchmark had a small bug in it. There was a global array, and every time it went around the loop, it put some data, not a small amount of data, in fact, into that global array, but it never emptied the array. So its memory use just kept increasing over time. And after a couple of seconds, it used, well, 1.82 gigabytes of RAM and caused the VM to crash. It's okay, so I read up enough JavaScript to work out how to empty the array on each iteration. And I published a very simple pull request to Optane saying, here's how I fixed it. And I gave lots of graphs to explain what was going on and why I fixed it. So that was in October 2016. About a year and a half later, someone from the V8 team said, sorry, Optane is a bad benchmark suite. We no longer recommend it being used, and so we don't want to fix the bug because that will encourage people to use it. And I thought, oh, that kind of sucks. Like, it always makes me feel a bit unhappy when there's incorrect code on the internet. But, you know, fair enough, if the benchmark suite's no longer being maintained, okay, I can understand why. Fast forward to early 2019, and the V8 team published what is my favorite paper on Spectre. If you haven't read it, it's brilliant. It's really, really great. And as part of that, they published a blog post. And the blog post is totally worth reading. But I noticed, as I got down near the bottom, you'll see the bit that I've highlighted in red, they said, if we turn on all the sort of maximal Spectre mitigations to try and prevent timing attacks, it makes the Optane benchmark suite slow down by 2 to 3 times. And I thought, huh? But you said the Optane benchmark suite shouldn't be used anymore, but here you are using it and making big decisions based on it. Now, I don't want to bash the V8 team. I actually like their work a great deal, and I think they're really good people doing really good work. But I think that this shows an assumption here, which is that the benchmark suite, Optane in this case, had outlived its usefulness. But I don't think that's the case. And let me give a sort of formal definition of why I think that's not the case. In a formal sense, a benchmark suite is a finite representation of the infinite possibilities of behavior. Now, what does that mean? It sounds rather complicated. Well, there are an infinite number of programs I can write in any programming language, and probably an infinite number of different ways that you can structure programs such that you need to optimize them in a different way to be most effective. A benchmark suite contains a fixed small number of programs. So by definition, it must be representing a subset of the infinite possible behavior that I could express in my programming language. That means, by definition, every benchmark suite is going to be imperfect. Frankly, every benchmark suite is going to suck. They're never going to tell us all of the possible things that people might write, all of the possible ways that people might write programs. It's just not possible. And as soon as you realize that, in my opinion, it changes the way that one should think about a benchmark suite. I think we just need to have more and more benchmarks. My rough guess, and this is very much a rough guess, is that most language implementations have one or two, at least orders of magnitude, too few benchmarks. In other words, we almost always don't have enough benchmarks. And in nearly all cases, more benchmarks gives us a better understanding of the performance of our language implementation. So I don't want you to throw out Octane, I want you to keep it and add another benchmark suite. And now I've got 2 benchmark suites and life is better. There is one small qualification to this that I do want to add in case people wonder. In nearly all cases, more benchmarks is good. The only exception being if you have endless benchmarks that are effectively the same benchmark in disguise. In other words, imagine I take a benchmark, copy it, and just change the constants. Well, it's technically a different benchmark, but it probably behaves in exactly the same way as the one before. If I have too many benchmarks that are effectively identical, that will distort my idea of the performance of my language implementation. But that doesn't happen very often. Provided we don't do that, more benchmarks are nearly always good. So I think your benchmark suite is good, my benchmark suite is good, and put them together, we have something even better. Another assumption, which is that programming languages on virtual machines, or indeed some ahead of time compiled languages too, are safe because Java, for example, doesn't let you express buffer overflows, nor does Python, nor do many other ahead of time compiled languages. And so because the term virtual machine is overloaded, and that confuses some people, sometimes people say, actually, languages like Java are managed languages. They're managed so that they can't do wrong things. These are the published CVEs for Hotspot running up to the end of 2019. In other words, how many published security attacks were there on the JVM? And it varies a lot year to year, but I'd say the average per year is around about 100 CVEs. Which you can see on the left. If I look on the right, we can see that actually we do get things like buffer overflows and memory corruptions. And these are happening to Java programs. And there are some other great ones. I have no idea what bypass something actually means. It sounds entertaining. But why are we getting bugs in these languages that appear to be impossible? Well, it's kind of obvious, isn't it, I suppose? Things like Hotspot are implemented in C or C++, and everyone knows that C and C++ are a shotgun aimed at everyone's collective feet. They aren't safe languages. If we implement a safe language in terms of an unsafe language, we'll inherit some of that unsafety. And it doesn't seem we can do very much about that. And indeed, the situation's worse for virtual machines than ahead of time compiled languages, because virtual machines are generating machine code at runtime and executing it. And that is a whole new world of potential problems. And indeed, I think the attack surface of VMs is much greater than ahead of time compiled languages. And I'm a little bit worried because I think up until now, the bad people, the sort of hackers in films who are in a basement with all the windows closed with about 17 computer monitors trying to break systems, mostly have been looking at C-style programs, and I think they've only just started turning their attention to the virtual machines of this world. I think once they start looking in more detail, they're going to find increasing numbers of problems because mostly virtual machines have prioritized performance over safety. So I'm worried that there could be a big security sequence of bad things happening in the future. I hope I'm wrong. But when you speak to virtual machine developers, they often say, we know C and C++ are very dangerous and we only have 8 toes left, but we're stuck with it. We can't do anything better. A reasonable question is, what happens if we can use a safer language to implement these things in? And the obvious candidate at the moment is Rust. So for those of you who are probably at least somewhat aware of it, Rust is a systems level language that doesn't have malloc and free, but also doesn't have a garbage collector. And some VM teams have evaluated Rust and they said, yeah, nice idea, but it won't work because its performance model is too different from what we know we need from C and C++. So in my group, we thought, okay, what happens if we try and use Rust to write virtual machines in? How far can we get? Can we make it a good fit? Well, one of the immediate challenges you come up with is inside a virtual machine, you tend to represent language level objects as dynamically dispatchable things. In other words, if you're implementing, say, JavaScript, you'll have a type called object, and then you'll have subtypes integer and string and file, And when you call a method on those at the user language level, you'll actually dynamically dispatch a call inside the virtual machine on those things. Here's some Rust code that shows that this works a little differently in Rust than you're used to. This code, real Rust code, it really executes correctly. And let me show you a few of these things to understand what they mean. Let's look at this first assert statement. What it says is the following. Ampersand means give me a pointer to. So it says the size of a pointer to a Boolean is the same as the size to a pointer to a U128. Exactly the same as it would be in C. The second assert statement says the size of a pointer to a Boolean is the same as a machine word. Exactly the same as in C again. The third line is where things get weird. This says the size of a pointer to a dynamically dispatchable type, that's what ampersand dy means, is 2 machine words big. That's completely different to C and C++, where this would also be 1 machine word big. What's going on? Well, it turns out Rust makes a very different decision over dynamic dispatch than previous languages. It says that a type T only has to be dynamically dispatchable if you explicitly want it to be. And we can use this unsafe transmute call to break apart one of these 2 machine words big things into 2 pointers, one to the data pointer and one to the V table. Now that's very nice and good, but it's probably not the right performance model for virtual machines where we store dynamically dispatchable pointers everywhere. This would basically double the size of the heap, especially when we have aliasing. So can we do better? Well, good news, yes we can. And I'm not going to go into all the details of this, but this is pretty much the complete implementation you need to solve that problem if you care about it. We make a new type called thin pointer, which is always going to be 1 machine word big.
So, sorry, Laurence.
Yeah, go ahead.
Could you turn on the laser pointer or something? It's quite confusing because well, on my screen anyway, your cursor doesn't correspond to where you're pointing.
Oh, unfortunately, I do have a laser pointer, but I don't know how it's going to work well. Can you see the little hand on the screen?
No, there's no. Are you on PowerPoint? Can you not do a right click?
No, I'm in Adobe. I wonder what else I can do.
Okay, never mind. Okay, all right. Okay.
I'm really sorry about that. What else can I do?
Okay.
If anyone has any suggestions, let me know. Thank you for saying. Okay, so I'm currently pointing. This is going to be quite fun. Where it says FN new thin pointer. What this function does, it takes in one of these 2 machine word size pointers. It then uses the transmute call a couple of lines below, breaks them into 2 things, and then it allocates something on the heap and lays it out more or less as C++ does. It puts the vtable pointer first, then the data. At the bottom where it says impl dref for thin pointer, blah, 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 given a thin pointer, that converts it back into the double width pointer that Rust needs to do dynamic dispatch. So don't worry too much about the details, but it's possible. And that then allows us to implement one of the classic VM operations, which is I've got an object in my language and I want to know, is it of a particular type? Is it an integer in the language or not? It's often called something like try downcast. And we can do this as quick as you can in C and C++, which is good because it turns out you use this all over your virtual machine where you say things like, I've got an object V in FNF. Is it an integer? If so, print it out, otherwise do something else. So the point here is we've been able to bend Rust in the same direction you've got from C and C++. And yes, it requires some unsafe code, but we've managed to mostly wrap it in a safe interface and give you fewer ways of shooting yourself in the foot. So can we use Rust for virtual machines? Good news, so far so good, and I'll give you a few more details about this later. We have 1 medium-sized interpreter for a kind of Smalltalk style language that runs faster than any of the other interpreters written for that language in C or C++ and so on. We have an gradually improving garbage collector for Rust, so we can retrofit garbage collection on it. There are some trade-offs there, but it does work. And we have a system that can run these things at a sort of hello world level. So it's kind of working. Let me move very briefly on to another assumption, which kind of relates to what we said earlier about the security landscape. And this relates to pointer sizes, because I think the processors of the future are not going to look exactly like the processors we currently have. Some of you may have heard of Cherry, which is a capability instruction set from the University of Cambridge. ARM are currently making a new processor that has this built in. It has double width pointers. And in those extra bits, the extra machine word, are permissions telling you what you can do with that pointer. Now, this is really appealing for virtual machines because it means we can probably start to lock down things like the just-in-time compiler and the garbage collector and make sure that we move away from the current model where every part of the VM has equal access to everything else to a situation where we've compartmentalized the VM into parts of differing permissions, and we can hopefully remove some of the security problems before they ever happen. And I think there's going to be more stuff like this in the future. This is pretty much my final assumption before I give you a brief taste of some of our research work, which is that we're good at explaining what we do. I wonder if anyone here knows what all of these things share in common. Shout out if you recognize what the commonality is. So no one's quite sure. They're all Python implementations. Those are all of the publicly known Python implementations as of a year ago. There's at least one more since then, and there is at least a couple more non-public Python implementations to add to the list, at least. Why are there so many implementations of Python? Well, it's because people look at CPython, the normal Python, and go, it's quite slow. I am very clever. Ergo, I can make a faster implementation than CPython. And if I take, for example, Unladen Swallow as an example, that was a project at Google a few years ago, quite well resourced, to create a new version of Python that statically compiles everything to LLVM. And LLVM is amazingly good at optimizing static programs, right? This clearly is going to make Python programs run so much faster. But when this happened, there are a couple of us who just went, oh God, not this again, because we know that compiling dynamically typed languages to a statically typed language doesn't give you good performance. You'll get, if you're lucky, about a 20% performance increase. It never has worked. It's never going to work because there's so much stuff left in the statically compiled program, dynamic type checks and so on, that you can't remove, that it completely kills LLVM's ability to optimize everything. So I think the reason that this happens is that we often pretend that we've told people all of the lessons we've learned about language implementation, but we haven't. I know that this doesn't work. Probably many of you on this call do. But where's it written down? I don't know. I'm not sure it's ever written down. It's just folklore passed amongst people in projects. And part of that is because we often pretend there are no trade-offs in language implementations. The classic example to me of this is if you read benchmarks for virtual machines, the performance numbers they present are always in terms of the steady state after all the JIT compilation has happened. They never tell you how long it took to warm the program up. But users always perceive warm-up and often care a great deal about it, and often they complain that that's causing them bad performance. They often don't know that's the cause of the bad performance, but it often is. By not telling them about that, we make our lives much easier, and we also make it much harder for people coming into the field to really understand what's going on. This is a little better for ahead-of-time compilers. There are more textbooks and more written material, but actually I still think it's a really hard field for people to get into. VM's even harder again. So where are we? Because I've kind of given some kind of depressing news, I think, in some sense. I think we understand less about language implementations, particularly virtual machines, but also, in my opinion, ahead-of-time compilers, than we should, than we could, and less than we need to. There are some clear problems, some things that we clearly should look at sooner rather than later, and I bet you there's a whole load that I haven't even thought of where there are problems. But I'm an optimist. To me, this is really good news because that means there are opportunities. People are often happy with our language implementations, even though those implementations are not as good as they should be. That means if we improve our implementations, people are only going to get more and more happy. And so my idea for one way of doing this is a project that we're working on called hardware meta tracing. And I'm just going to give you a sort of 2 or 3 minute explanation of what we're trying to do to find new ways to make languages go fast. So I referenced this earlier. This is a simple interpreter. Don't worry about the details. It's a simple interpreter for some imaginary dynamically typed language. So the sort of thing a final year student would write. And you give an interpreter like this to a meta tracing JIT, Then you give it a user program, which you can see on the right-hand side. And the way that these systems work is that when they realize that the program on the right-hand side is part of a hot loop, they record what the interpreter does, convert that to a trace, optimize the trace, and then convert that to machine code. Now, this is a totally weird idea, so let me give you a diagrammatic representation. In one of these systems, you write an interpreter, you execute your program. You find a for loop or a while loop or a function call that's hot, and then you enter the tracer to record what it does. You record what that loop does, compile it into machine code. And then you can always execute the machine code in place of the interpreter for that given loop. Now, that loop will contain if statements because it's by definition a linear version of the control flow for that program. So there will be parts of the machine code that said, there's a condition here, and if it fails, there's no machine code. That's called a guard failure. And if that happens, you have a very weird component called the black hole interpreter, which is basically a way of getting you somehow safely back to the interpreter so you can begin the whole process again. It's a really cool technique. But imagine I say that the interpreter has performance 1x. If we're lucky, the machine code will be about 10x faster. That's good. But to get to the machine code, we have to go via the tracer. And that's currently a software-only component in existing meta tracing systems, and it slows execution down by about 100 to 200x, depending on the system, blah, 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 blah. That's so slow that in these systems, you're actually nervous of ever executing the tracer, because if you run it and it doesn't pay off, you've paid a huge penalty for no gain. What we are looking at doing is, first of all, moving this whole system into Rust, and then we're moving the software tracer into hardware. And we're using a feature that's in, for example, in existing Intel chips, it's called Processor Trace PT, that allows us to record the jump instructions a program takes. We're using that to recover the control flow graph a program took, and we're using that to do our trace compilation, JIT compilation, however you want to call it. And we're expecting the overhead to go down from about 200x to 2x. There's a little bit of hand waving in that, but that's our rough aim, because PT has about a 5% overhead. So currently, we've been working on this for a little while, and we can now execute Hello World in terms of generating machine code in this system using processor trace inside Intel chips for a very simple interpreter for a simple language. At the moment, it's incredibly slow, but the good news is everything is working. All of these big bits that no one had tried putting together before, they're working. So this is where I think there's huge potential, because this, if we're successful and are able to scale it up, will enable many more languages to run fast and to be made to run fast very cheaply. I want to thank EPSSC in the UK and our industrial funders who funded a lot of the research that I've mentioned, sometimes in passing. And I'd like to thank you very much for listening. And if you have any questions, I'd be very happy to take them. Thank you.